Okay, hello everyone. My name is Shai Mohan and I will present the paper Boosting Simple Learners. And this is a joint work with Noga Alon, with Alon Gonen, and with Elad Khazan. Okay, so this paper is in machine learning. Specifically, we learned that we consider the setting of pack learning, binary classification. So we assume domain X, there is an unknown target concept, which is just a binary function from X to plus minus one. There is also an unknown distribution D over X. Our algorithm gets an independent sample of examples drawn from D with their labels according to C. And the goal is to output an hypothesis H, which agrees with C on most examples, on most points, with respect to the measure D. Okay, so the probability that H and C disagree should be as small as possible. Now, boosting is an approach for binary classification in which one assumes an oracle access to a weak learning algorithm. This is an algorithm that achieves a non-trivial loss. Okay, so given a sample, it it outputs an hypothesis that agrees with the target concept on just a little bit gamma more than half of the points according to the measure. And given such access, what boosting algorithms basically do is that they repeat t times. So they basically apply the weak learner W t times on carefully chosen subsamples. And then they aggregate the weak learners, these weak hypotheses B, the results, into their final predictor. And the intuition is that one focuses on hard examples, right? So maybe first the S1, the first sample that you apply W on will just be a uniformly drawn sample from S. And then the boosting algorithm usually checks where the weak learner made a mistake, where he didn't make a mistake, and then it produces the next sample and so on and so forth. Now this is really useful, this idea, when it's relatively easy to come up with these weak learners. So with these rules of thumb, with these weak learning rules that give you slightly better than random. So this is used, for instance, in spam detection. So here you can think about weak hypotheses. Maybe they can be like they just look for some phrase, some trigger phrase, like apply now, this is in junk, Nigerian print, etc. And then once you have this weak hypothesis or weak learner, you can use boosting to automatically aggregate these rules to a very accurate rule. Another famous example is in face detection. This is called the Verlaine-Jones framework, and it's one of the most famous applications of boosting, I think, in practice. Here, the task is to do face detection, and the weak hypothesis here basically they sum the pixels in rectangular areas, and when boosting aggregates this weak hypothesis to very, very good and accurate detectors, face detectors. Okay, so from a theoretical perspective, boosting has been considered since the end of the 80s, so just a little bit after the definition of pack learning by Valiant. And the original formulation of boosting was the following. So assume we have a target hypothesis class H. So this is a class of concepts. And assume that we have a weak learner for H in the sense we explained earlier. So for every distribution D on the domain and for every target concept from H, the weak learner, given enough examples, will output a weak hypothesis B, which agrees with the target concept on slightly more than half of the points. And then the goal of boosting was to learn concepts from H to arbitrary precision, right? So to get a strong learner, but for the very same class H, right? So we begin with a weak learner for H, and we want to learn to produce a strong learner for the same class H. The perspective of this paper, of our work, is different. How is it different? So we assume a base class of weak hypothesis, which we think of as a simple class. So each hypothesis in the class is computationally bounded. It's some simple object, simple classifier. And we assume that we have a weak learner, which is a strong learner for the base class B. So it can be an empirical risk minimizer for B, right? So given any distribution D and any target concept C, which may be well outside B, our strong learner, our weak learner, which is a strong learner for B, will output an hypothesis, which is the best approximation to the target concept inside the restricted class B. And the goal is to learn concepts which are far from B to arbitrary precision, right? So we want now to really to aggregate this weak hypothesis to be able to approximate concepts that are well outside B. So we want to boost the class. We're given a strong learner for a small class, and we want to produce a strong learner for a much bigger class. So we boost the kind of learning task we are able to do. So the questions we consider are, first of all, in terms of expressivity, given a simple base class B, what concepts can be learned? Can at all one learn concepts that are far away from B? Can you really do interesting boosting under this assumption that the base class B is limited? And the answer is yes. The answer is that under very mild assumptions that are essentially satisfied by any class, any non-trivial class considered in the literature, yes, you can approximate arbitrarily complex concepts using boosting with an agnostic learner for B. The second question is, does this assumption that the base class, the weak hypotheses are limited or computationally restricted, does this assumption change classical results? Does it affect classical results in the theory of boosting? And surprisingly, the answer here is also yes. So there is a classical oracle complexity lower bound by Freund and Shapira, which we are able to circumvent using this assumption. Okay, so now I'll tell you a little bit more details about each of these results. So we'll actually begin with number 2. First let me formalize how do we quantify the assumption that the base class is limited, is restricted. So we simply assume that the base class is a VC class, namely that it has a bounded VC dimension. Okay, that's our assumption. That's the only assumption we make on the base class, right? So we have an agnostic learner for a base class, whose VC dimension is bounded, is small. And this is really inspired by the convention that weak hypotheses are rules of thumbs from an easy to learn class, right? Because we know that if the VC dimension is constant, then the class is easy to learn in the PAC sense. And therefore, we quantify it using this parameter. And for those of you who don't know what VC dimension is, let me just mention that it is a combinatorial parameter which characterizes the PAC sample complexity of a class of functions. Right? So it is exactly the dimension that tells you how easy it is to learn a class in terms of sample complexity. Okay. So now I'll tell you about our results in more detail. So we'll first discuss the oracle complexity result. So for this, let me first tell you what is the lower bound that we are able to circumvent. So Freund and Shapira proved the following limitation on any boosting algorithm. So for any boosting algorithm G you give me, and for any gamma greater than 0, recall that gamma is the advantage G has over 1/2, they can cook a weak learner W, so there exists some particularly bad weak learner W in the target class H, such that W is a gamma weak learner for H. So W and H satisfy the weak learning assumption. However, G must invoke W many times, at least 1 over gamma squared, in order to achieve a constant loss, let's say less than 0.1. So this is very nice because AdaBoost achieves a matching upper bound. So it shows a sense in which AdaBoost is optimal. However, if you carefully inspect their proof, you see that it is derived using the probabilistic method. And in particular, the implied class of hypotheses that are used by the weak learner, right, the weak hypothesis, has a super constant VC dimension. The VC dimension goes to infinity as gamma goes to 0. And we see that this violates the working assumption we have, right? So this theorem does not apply if one assumes that the class of weak hypothesis is simple in the sense that it has a small VC dimension. And therefore, it is natural to ask whether the lower bound holds also when W satisfies our working assumption. And it outputs simple hypothesis from a VC class. And what we show that the answer is no. If you know that the VC dimension of W is small, then you can actually improve the oracle complexity, number of times you call the weak learner, quadratically from 1 over gamma squared to 1 over gamma. And the, the first idea, maybe the basic idea, is to allow for complex aggregations. What do I mean by that? So most previous boosting algorithms, they output an hypothesis, which is simply a weighted majority vote of the weak hypothesis outputted by the weak learner. Right, so this applies to boost by majority, AdaBoost, LP boost, total boost, many boosting algorithms. They do this kind of aggregation. We will use more complex aggregation rules. So what is an aggregation rule? An aggregation rule is simply a Boolean function. It gets t bits, the prediction of each weak learner outputted by the weak learner, each weak hypothesis outputted by the weak learner, and it outputs a bit, which is our prediction of the final hypothesis. Okay, so the final predictor is given, maps labels x by g of b of x, where b of x is this representation vector according to the BIs, right? So the weak learner gives us this list of weak hypotheses, B1 up to BT. Then we think of this vector as a representation vector of a point X. And G applied on this vector gives us our prediction rule. So as I told you before, the most famous aggregation rule in this context is a weighted majority vote. But you can also take polynomial thresholds, right? So take a threshold over a polynomial function rather than a linear function. Or you can take decision trees and many other options. And we will use complex aggregation rules as I'm not sure we'll see it today, but let me tell you that at least. Okay, so what is our strategy? So the one kind of observation that guides our algorithm, the algorithm that circumvents the lower bound, is that we want to obtain an interpolating aggregation rule. What does this mean? So recall that our boosting algorithm gets as an input a sample, a labeled sample. And what we will do is we will basically try to get the weak learner to produce a weak hypothesis until we can aggregate them in a consistent way, in a way that interpolates all the input examples. And the way we achieve it is by separating all opposite labeled pairs. Okay, so we summarize it in a lemma or an observation. So the following are equivalent. There exists an interpolating aggregation rule, right? So you can aggregate the weak hypothesis in a way that interpolates the data, if and only if all opposite labeled pairs are separated, namely for every xi and xj that have different labels, there exists one weak hypothesis which separates them. So this will be a strategy, and the strategy gives rise to this meta algorithm. So we basically repeat until we separated all opposite labeled pairs. So at each point, each time step t, we define a distribution dt on the input sample, where each example xi is assigned a probability which is proportional to its degree. What is the degree of a sample? The degree of a sample is the number of j's that have opposite label from it and are not yet separated from it. And then, a simple analysis shows you that that in each round, a gamma fraction of the remaining unseparated pairs are being separated. And therefore, since the total number of pairs is m squared, right? We have an example, a sample of length m, and in each step we get rid of 1 minus gamma. We get rid of gamma of the pairs. So in total, the number of rounds will be log m over gamma. And again, the crucial point is that the dependence on gamma here is linear rather than quadratic, as in other boost. Okay, so that's the first main result. So the takeaway message, I think, is that if you utilize the assumption that the base class is restricted, then you can improve on you can circumvent classical lower bounds. In particular, we demonstrated how to improve this Oracle complexity lower bound. An interesting property of our algorithms, it requires relatively complex aggregation rules. We did not discuss it, but if you come to the poster, I'll be happy to give you more details. And also, yeah, we did not discuss generalization. Yeah, so the rest, generalization and how complex the aggregation rules are, I will discuss with those of you who will come to the poster session. Okay, so now let me tell you a little bit about the second main result, which is about expressiveness. Right, so the question we ask here is what can be learned by boosting simple base class. Right, so recall that we have a base class B, and we assume that the weak learner is a strong agnostic learner for B. So it gives us always the best approximation in B. And the question is, what can we learn with it? Like, can we really learn concepts that are far away from B? Can we really boost it in a meaningful way? So to answer this, let us first rephrase the weak learning assumption in a way which is more convenient in this setting. So one can show that the weak learning assumption, the classical weak learning assumption, amounts to the following definition: gamma realizability. So let us say that a sample S, labeled sample S, is gamma realizable if for every distribution D over the xi's, there exists some weak hypothesis in B, which is correlated with C according to this distribution, right? So it agrees with C on at least a 1 plus gamma over 2 fraction with respect to this distribution. So gamma realizable samples are exactly the legal inputs for boosting with advantage gamma, right? So if we have an agnostic learner and we set the error parameter to be gamma, the advantage parameter to be gamma, so these are exactly the inputs for which running boosting with it will produce a valid output function. Also notice that when gamma equals 1, this specializes to the standard definition of realizability with respect to B. So this means that really the sample is labeled by some function in B. Now the first main result in this context, which is also, it's very simple, but I think it's important, is that almost every base class can be used in boosting to express arbitrarily complex concepts more formally. So assume B satisfies two very easy to satisfy conditions, which I will tell you soon. But Once it satisfies these mild conditions, then for every sample S, there exists some positive gamma such that S is gamma realizable. Right, so this means that once S satisfies these mild conditions, then every sample S you give me, I can pick a gamma which is positive, and then once I run boosting, any boosting algorithm using a gamma weak learner, so an agnostic learner with accuracy gamma, then I'll be able to interpolate this input sample. Okay, so now what are these two mild conditions? So the first one is symmetric. So you want that B will be closed under negation, and this is trivial to satisfy. The other one is full rank. So for every sequence of points, every set of points, x1 up to xn, if you look at the binary vectors b of x1 up to b of xn, where b ranges over all concepts, all weak hypotheses in B, then this set of binary vectors has rank n as a real matrix. And notice that these conditions are satisfied by any class which contains singletons or one-dimensional thresholds, right? Then you get a triangular matrix or the unit matrix, which are full rank. So this is really easy to satisfy. And once you satisfy it, then really you are able to approximate any sample, any target sample, and also one can formulate theorems that you can actually learn anything using boosting such weak learners. Okay, so qualitatively we answered like basically as long as B satisfies these conditions, and in the limit when gamma goes to 0, you can learn anything. But we want to understand this more qualitatively. So what can be learned for a fixed gamma? Let's say we have a gamma agnostic learner for B. How large is the class of concepts that we can learn for a fixed gamma? And at what rate does this class grow as gamma goes to 0? So we define the following combinatorial measure to quantify the richness of this class, the gamma VC dimension. So the gamma VC dimension is the largest integer D for which there are x1 up to xd, such that every binary pattern over the xi's is gamma realizable by the class. So this is basically the VC dimension of the concepts that one can learn by boosting with advantage gamma. Okay, so when gamma equals 1, it's just the VC dimension of B. And when gamma goes to 0, it goes to infinity. Okay, so it's the VC of concepts that are gamma correlated with B. And then we ask how large can the gamma VC dimension be? How small can it be? And we prove general bounds, or we prove that that the gamma VC dimension in general it is no more than d over gamma squared, where d is the VC dimension of the base class, and we are able to slightly improve this bound, but then we get worse dependence on the VC dimension. But okay, I don't really want to into all these details, all these technical details. So let me, so let me just summarize, and I'll invite you to see more quantitative bounds in the poster session. So we revisited boosting under the assumption that the base class is restricted, is a VC class. And the first one result I showed you is that using this assumption gives rise to a different landscape of boosting, and in particular, you can circumvent a classical lower bound on the oracle complexity by finding Shapiro. And the second result was about studying how expressive certain base classes are when used in this framework. So how fast can you learn faraway concepts in this framework? And we defined the combinatorial parameter which extends the VC dimension to this context, and we analyzed it for various classes Let me just note that there are many open questions, so we don't have tight bounds on the gamma bits dimension, even for the most basic classes such as the half spaces. And I invite you all to discuss it with me further in the poster session. Thank you very much.